All right, in this example, it's going to be very similar to the last one. It's a normal tangential problem, just like the last one was. So what we have is this bowl, this parabolically shaped bowl, and there's a mass, which you can make out up here. And it starts off in the bottom of the bowl, but as we spin the bowl, it slides up. The idea is that it slides up to here. And in this particular example, it's staying there. All right, so what do we know? We know that mg for that block is 6 pounds, and it's at rest relative to the parabolic dish, which means it's neither sliding up the dish nor down the dish. And so the idea here is that the acceleration is not going to be up or down the dish. There'll still be the centripetal acceleration, but there's no sliding going on. It also tells us that we're at a static frictional case. It's rotating at a constant rate, so this omega in here, or theta dot, is constant. And the coefficient of static friction is given. Mu static is equal to 0.5. The radius, that means the distance out from the center, is equal to 6 feet. And then the maximum allowable speed, what that says, if it's the maximum allowable speed, we're right at the point where it wants to slide up. And that tells me that the friction is down. It also tells me that when F static is less than or equal to mu static times the normal force, at this maximum point, my inequality becomes an equality. So the static frictional force equals mu s times the normal force in this particular scenario. So we're going to put an equal sign in here. All right, so what are the forces acting on this object? Well, of course, I'm going to have mg, and that's equal to 6 pounds, but that's a gravitational force due to the Earth acting on the block. And there's a normal force perpendicular to the surface. Of course, it's a parabolic surface, so we're going to have to ask ourselves what perpendicular is, and we'll answer that in a second. So that's a normal force due to the dish acting on the block. And then, of course, there's a frictional force. Now, at the maximum allowable speed, the block wants to slide up. Anything faster and it's going to slide up, and so the frictional force must be down. So F static, also due to the dish acting on the block. All right, so now we need our coordinate axes and our acceleration. The acceleration is going to be strictly in the inward direction. That's a normal direction. Not normal to the surface, but in the normal direction, the inside of the curvature. You got to be careful of our terminology. So I can say then that this is E normal. E tangential in this drawing would be into or out of the page. We're not going to worry about that. And then up is the y direction. So there's the y direction here. The acceleration is strictly in the normal direction. But like in the last problem, I need to figure out what my angle is. Well, how do I find my angle? Well, remember that we can find tangent to the curve, because we know the equation y equals r squared over 12, and so in this direction there's some angle theta, but the tangent of theta, hence tangent to the curve, is equal to the rise over the run of this curve. Well, that's delta y over delta x, or calculus dy dx. And actually I shouldn't say x, I should say r. Well, if y is equal to r squared over 12, dy dx is equal to 2r over 12, or r over 6. And in my case, that's equal to 6 feet. And so what that tells me then is the tangent of theta, which is dy dr, is equal to 6 over 6, which is 1. So the tangent of theta is equal to 1. So of course theta is equal to 45 degrees. So if this is 45 degrees in here, that's theta equal to 45 degrees, then this must also be theta, and this must also be theta. So I've got a couple of different thetas in here. I'm going to get rid of that for now. And we're ready to write out our force equations. Now you'll notice that the normal force has a component in the normal direction, and the frictional force has a component in the normal direction. The normal force, that's going to be F normal times the sine of theta. It's opposite the angle theta. the frictional force is going to be Fs times the cosine of theta because it's adjacent to the cosine of theta. So as I write out my force equation, the sum of the forces in the normal direction, I'm going to have Fn sine theta plus Fs cosine theta equal to mv squared over rho. And actually we've called it r in this problem, so mv squared over r. Then the sum of the forces in the y direction, I have Fn cosine theta. Notice Fs is down, so Fs will be negative as far as that sine of theta is going to be concerned. So minus Fs sine of theta, that's down, minus mg, and all that's going to equal 0 because the acceleration is only in the normal direction. Well, once again, keep in mind that F normal times the coefficient of static friction equals Fs. Fs is equal to mu s times F normal. So if I rewrite the y equation, I get Fn cosine theta minus mu static Fn sine theta equals mg, bringing the mg to the other side of the equation. Or I can write it this way, Fn times the cosine of theta minus mu static times the sine of theta equals mg, or Fn equals mg over cosine theta minus mu sub s sine theta. And then I'm going to substitute this normal force into the equation in the normal direction. So I'm going to get mg over cosine theta minus mu static sine theta times the sine of theta plus Fs, but Fs is mu s times the normal force. So that's going to be mu sub s mg cosine theta over cosine theta minus mu static sine theta equals mv squared over r. And notice, very similar to the last example with the race car, the masses all cancel out. So the mass of the block really has nothing to do with this problem. It doesn't matter. The mass of the block does not matter. All right, I'm looking for the allowable speed. I'm looking for the velocity v. So there it is. So I'm going to bring the r over to the other side. Rg, and then I get the sine of theta plus mu static times the cosine of theta. And notice the denominators are the same in both terms. So cosine theta minus mu static sine theta. All of that's equal to v squared. And so if I start working this out, r is equal to 6 feet. G is 32.17 feet per second squared. Sine of 45 degrees plus mu s is 1/2 times the cosine of 45 degrees. And all of that is over to the cosine of 45 degrees minus 1/2 sine of 45 degrees. V squared will be 579. And I have feet per second squared, so that's feet squared per second squared, which means my V is 24.06 feet per second.